Good day, I'm Norman Wahlberger. In today's video we're going to look at this concept of complexity of natural numbers, and in fact we're going to look at a couple of different versions of complexity, one associated to the exponential operation, the other associated to the triangular operation, sort of one step up. And what I want to slowly move towards is this idea that the natural numbers are a lot more complicated than we think they are. And that doing arithmetic, especially with bigger and bigger numbers, starts to look very different from doing arithmetic with usual relatively small numbers that we're mostly concerned with in everyday life. So this is a bit sobering, and it's maybe a little bit disorienting as well. Some of the insights that we're going to gain by thinking about this concept of complexity. Okay, so the first concept is that of exponential complexity, and we define that to be the minimum number of symbols used in a meaningful arithmetical expression that evaluates to a number n. So n is a natural number, and its exponential complexity is the minimum number required to have an arithmetical expression that evaluates to n, where we're only using the following symbols: the digits 0, 1, 2 up to 9, together with addition, multiplication, exponentiation, and a left and a right bracket. And we're obliged to write an arithmetical expression as a sequence of symbols, a string of symbols, which have a meaningful arithmetical content. So, for example, the exponential complexity of 14 is 2, because it takes 2 digits to write 14. 1024, we saw its complexity was 3, because we could actually write it in this slightly more efficient way here by using the exponential sign. So 4 exponent 5 is another way of writing 1024. Instead of using 4 digits to express it, we're using 3 digits to express it. So its complexity in this framework is 3. How about this somewhat bigger number, 371293? Well, it turns out that its complexity is 4 because it happens to be a perfect power. It's 13 exponent 5, or 13 to the 5. Now, if we're not that familiar with our exponents, we wouldn't perhaps guess that this particular number is an exponent of this kind, a rather special kind of number. So the usual guess that we would suppose is that this is probably of complexity 6, because we generally feel that typically most numbers are going to have complexity the same number of digits that are used to express them. That's at least only an intuition. We want to make that a little bit more precise, and we will make that more precise in our next video. Okay, what about this number here, 69735688807? Well, you might think that its complexity is 3, 6, 9, 10, but its complexity is probably 8, because we can write it this way, as 2 times 3 exponent 20 plus 5. And we're using the convention here that exponentiation has precedence over multiplication. So this is an unambiguous statement, which means that you take 3 to the 20, and then you multiply that by 2, and then finally you add 5. So here we need 1, 2, 3, 4, 5, 6, 7, 8 symbols. And my guess is that that's probably the minimum required. But actually I'm not entirely sure about that, so we'll leave a question mark over that. Probably the complexity of this number is 8, but it would actually involve some more work to verify that there wasn't some more efficient way of writing it, say involving some other power. Now, I'd also like to consider a slightly more sophisticated notion of complexity, which we're going to call triangular complexity. And that's the complexity that we're going to be mainly interested in for the rest of this video. So what is triangular complexity? Well, it's the same kind of thing where we're taking a natural number n and we're looking at the minimum length of an arithmetical expression for n, where now we're using this symbol set, which includes, in addition, the triangle operation. So they're all together 10, 11, 12, 13, 14, 15, 16 symbols in the collection of allowed symbols. And I remind you about the triangle operation. This is a hyper operation, which has this form, that m triangle n is m to the m to the m all the way up to the m, so a tower of m's, each exponentiating the previous, where there are n in the tower. There are n m's in this tower. So using this operation, we can of course create much bigger numbers much more efficiently than we can just with addition, multiplication, and exponentiation. So including this thing here will have a dramatic impact as we go to bigger numbers. But for relatively small numbers, like less than a billion or a trillion or so, it's not going to have a significant effect on complexity. But for us, complexity will mean triangular complexity. We want to go a little bit in this direction of including some of these hyper operations, and we're going to include this triangle one, which is also star 3 in my list of higher multiplications. All right, so a word of warning here that this notion of complexity, this triangular complexity, is in general quite hard to calculate, particularly if n is rather big. If n is very big, then there are all kinds of possibilities for using powers and combinations of powers and combinations of exponentials and triangles and just ordinary multiplications and sums and so on to cook up n. But for smaller n's, like let's say 1 to a billion or maybe a trillion, we'll see that this is not that hard in general. Okay. And so a tool for understanding that is to have a little bit more of a sense of what powers look like, both exponential powers and triangular powers. I'd like to spend a little bit of time now with you having a look at some powers. This is usually not done in mathematics. Usually these things are sort of over the hill and people are familiar with smallish powers but not much more than that. And I think it's really instructive to cast your eye over bigger powers to get just at least a rough familiarity with some of them. Maybe some of them will stick in your minds, and I think there's something beneficial about having this concrete contact with bigger numbers. That's my opinion. So I'm not asking you to memorize these, of course, but I just want you to have a look over them. Cast your eye over them, sort of read this. All right, so powers of 2, well, most of us are familiar with 2 squared is 4, and then we have 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th 128, 2 to the 8th is 256, 2 to the 9th is 512, and 2 to the 10 is 1024. Those are very important numbers that have come up in many different situations. And then higher powers of 2 are also important. 2 to the 11 is 2048, 2 to the 12 is 4096, 2 to the 13th is 8192, 2 to the 14th is 16,384, and 2 to the 15 is 32,768. Okay, I'm not going to read all of these, but let's have a look at, say, powers of 3. So the powers of 3 go from 9 to 27 to 81, then 3 to the 5th is 243, 3 to the 6th is 729, 3 to the 7th is 2,187, 3 to the 8th is 6,561, and then 19,683, 59,049, 177,147. Powers of 4, very closely connected with powers of 2, of course. 16, 64, 256, 1024, 4096, 16,384, 65, 536, 262, 144, 1048, 576. That one there. Powers of 5, 25, 125, 625, 3,125, 15,625. And then we see some higher powers. So please have a look at each one of those. So powers of 6. 6 squared is 36. 6 cubed is 216. 6 to the 4th, 1,296. 6 to the 5th, 7,776. And then 46,656. And then these higher powers also. Powers of 7. 7 squared is 49. 7 cubed, 343. 7 to the 4th, 2,401. 7 to the 5th, 16,807. And then you can have a look at these subsequent ones. Powers of 8. 8 squared is 64. 8 cubed is 512. 8 to the 4th, 4,096. 8 to the 5th, 32,768. And there are some higher ones. And powers of 9. 9 squared is 81. 9 cubed is 729. 9 to the 4th is 6,561. 9 to the 5th, 59,049. And some higher ones. Fun, isn't it? And just to go a little bit further, some powers of 11. 11 squared, 121. 11 cubed, 1,331. 11 to the 4th, 14,641. 11 to the 5th, 161,051. 12 squared is 144. 12 cubed, 1,728. 12 to the 4th, 20,736. 12 to the 5th, 248,832. 13 squared, 169. 13 cubed, 2,196. 13 to the 4th, 28,561. 13 to the 5th, 371,293. 14 squared is 196. 14 cubed is 2,744. 14 to the 4th is 38,416. 14 to the 5th is 537,824. And as far as we'll go, 15 squared is 225. 15 cubed, 3,375. 15 to the 4th, 50,625. 15 to the 5th, 759,375. So powers are interesting numbers. They are important numbers. They are arithmetically very compact ways of getting bigger sizes. Fermat's last theorem, of course, intimately connected with powers. So Fermat's last theorem says that, for example, if you take n equals 5, then x to the 5 plus y to the 5 equals z to the 5 doesn't have any integer or natural number solutions. It means that if we just look at sort of the list of fifth powers, that we can't find two of them on the list that add to a third one on the list. So it's all about these special kinds of numbers. But now we're also going one step further in this ladder of arithmetical operations to our triangular kind of exponentiation or triangular powers. And so it's useful for us to have a little look at some triangular powers. So I remind you that m triangle n means m to the m to the m, all the way up to the m, total number of n in the tower. That's what m triangle n means. So 2 triangle 2 would mean 2 to the 2, which is 4. 2 triangle 3 would mean 2 to the 2 to the 2, which is 16. 2 triangle 4 is 2 to the 2 to the 2 to the 2, which is 2 to the previous one, 2 to the 16, which is 65,536. What about the next one? 2 triangle 5. Well, at each stage, we are taking 2 to the previous one. So this would be 2 to the 65,536. This is getting to be a biggish number. It's not so big that my computer can't calculate it. In fact, my computer calculates it, spits it out in less than a second. And there are about 19,000 more digits between the first couple of digits, which are 2003529. Then there's about 19,000 more of them. And then the last few digits are 156736. So this is a very big number, but nevertheless, my computer can spit it out very quickly. We can still do arithmetic at the level of these numbers, but it's getting pretty big. If we wanted to go to the next one, 2 triangle 6, well then we would have to take 2 to this power And then we would be far beyond what our computer can do. So 2 triangle 5, yes, we can write that down. 2 triangle 6, we cannot write it down explicitly in Hindu Arabic form. How about 3 triangle 2? Well, that's 3 to the 3, which is 27. 3 triangle 3 would be 3 to the 27, and that's this number here, 765, 597, 484, 987. So that's hundreds, thousands, millions, billions. So 765 billion, 597 million, 484,987. And then the next one would be 3 triangle 4. That would be 3 to this number, and that again would be too big for us to contemplate. Not as big as 2 to this number, but still bigger than we would want to deal with. Okay, what about 4s? 4 triangle 2 is 4 to the 4, which is 256. 4 triangle 3 is 4 to the 4 to the 4, which is a reasonably big number. It starts 13407, and then there are 144 more digits, and then we end up with 084096. So these triangular kind of exponents or triangular powers, even for pretty small values of m and n, are pretty quickly big numbers. And pretty quickly, as we jack up this second sort of power, they get beyond what we're able to write down in our usual Hindu Arabic form. But we can still write them down in this triangular power form. And a few more. So 5 triangle 2 is 5 to the 5, that's 3,125. 5 triangle 3, which is 5 to the 5 to the 5, that's 1911, followed by about 2,100 digits, followed by 203125. 6 triangle 2, otherwise known as 6 to the 6, is 46,656. 7 triangle 2, 7 to the 7, is 823543. 8 triangle 2 is 167,77216. 9 triangle 2 is 387,420,489. And 10 triangle 2 is 10 to the 10, or 10 billion. 10 triangle 3 would be 10 to the 10 billion, or 10 to the 10 to the 10. 10 triangle 4 would be 10 to the 10 to the 10 to the 10, and so on. So by looking at this list of triangular powers, we see that with the exception of 2 triangle 4, which is 2 to the 16, that's 65,536, triangle powers do generally not affect complexity over exponential complexity for numbers which are reasonably small, say less than 10 to the 10. In other words, the advantage that you get by allowing yourself triangular powers as well as exponential powers doesn't really reduce complexity at all for almost all numbers less than 10 billion. Because something like 6 triangle 2 can also be written as 6 to the 6, or just 6 exponent 6. So in each case there's a complexity of 3. So you're not gaining anything. Here you are gaining something. 2 triangle 4, that's complexity of 3 in our triangular complexity system, while it would be complexity of 4 in an exponential system. Okay, so for relatively small numbers, there's not much difference between exponential complexity and triangular complexity, but for larger numbers, the effect is quite dramatic. We're able to express compactly bigger numbers dramatically more efficiently if we allow ourselves the triangle hyperoperator along with exponentiation. Now, I think most people's intuition is that the complexity of a natural number should be reasonably close to the number of digits of n, at least most of the time. Certainly we can state this proposition, which is immediately obvious, that the complexity of n is certainly less than or equal to the number of digits of n. If the number of digits is 20, then the complexity is at most 20, because we can certainly write it using 20 digits. We might be able to write it more efficiently, but certainly we're not going to require more than 20 digits. So this is obvious. The complexity of a natural number is less than or equal to the number of digits of n. And something else that's also very easy to see is that there's a connection between the complexity of a natural number n and the complexity of the next natural number n plus 1. The complexity of n plus 1 is less than or equal to the complexity of n plus 2. So if the complexity of some number n is 1,000, then the complexity of n plus 1 is at most 1,002. And the proof is reasonably straightforward. If n can be written as an arithmetical expression involving the k symbols, say S1, S2 up to Sk, so that's some arithmetical expression involving our various symbols, digits, operators, brackets, then an arithmetical expression for n plus 1 can be obtained just by taking the expression for n and adding the symbol plus 1. So that's an arithmetical expression for n. Then this will be an arithmetical expression for n plus 1. And this has 2 more symbols than this one does. So the maximum increase going from n to n plus 1 is 2. Now it might be that going from n to n plus 1 actually decreases the complexity quite dramatically, because it might be that n plus 1 is a perfect power. So then the complexity would go down quite a lot. So the lesson is that complexity increases slowly. As we move through the natural numbers one at a time, the complexity can go up by at most 2 every time. It never shoots up dramatically. But it can drop dramatically very quickly. So its upward movement and its downward movement are dramatically different. So here's a pretty interesting challenge for the computer programmers amongst you. It's an exercise to write a program that computes this triangular complexity C of n for n a natural number. So write a program that, say, given natural number in the range 1 to 10 billion, will crank out its complexity. Of course, there is a brute force program. There's a simple-minded way, which of course is very inefficient. Given a natural number n with, say, k digits, one way of determining its complexity is just to basically list all possible arithmetical expressions starting with the smallest ones possible and evaluate them all and see if any of them happen to evaluate to n. So you start with expressions of size 1. Okay, and you list all of them, see if any of them are equal to n. And if none of them are, you go to the expressions of size 2. Evaluate all of them. See if any of them are equal to n. If not, go to 3, etc. At each stage, there's only 16 possibilities for each symbol. So there's a finite number of possibilities, so there's a finite amount of work, but of course quite a lot of work. So eventually you will either get to the k digits itself, or you will find a shorter arithmetical expression which gives you the complexity. But that's not the program you want to write. Of course you want to write something that's cleverer, that uses the existing understanding of powers. So for example, let's give ourselves this task. Suppose that we have this number here. Alright, so this is 16,784,922, and we're interested in what is its complexity. So a first guess might be, well, 1, 2, 3, 4, 5, 6, 7, 8. Maybe its complexity is 8. We know certainly its complexity is at most 8. So a good place to start would be to factor this number. If we factor it, we find it's 2 to the 5th times 7 times 74,933. That's a prime. That's not much help to us. This is not close to being a pure power, so we can't immediately write down some more compact expression for it as a product of things or as a product of powers. But what we could do is we could look through our list of powers, like the ones that I showed you on the previous pages, and look through those things and see if we can find some combinations of them that give this thing here. Since this is a complexity of 8, it means that the combinations that we're looking for have to be relatively small. Basically, we have to look for something of the form 1 power plus another power. In fact, we can find such a thing. So it turns out, because I chose it that way, that this n is actually 8 to the 8 plus 6 to the 5th. And when we write it this way, which is a valid arithmetical expression, we see that its complexity here is 1, 2, 3, 4, 5, 6, 7, which is less than 8. And then I think if you look further at powers, you will likely find that you can't express this in a more efficient way. So I'm claiming that Cn is equal to 7, but I have to admit that I haven't actually looked at all the possibilities, because there are more possible powers that one could look at beside the ones that I've looked at. For example, it might be that this thing here could be maybe 34 to the 9 plus 7. Okay, if it was that, then that would lower its complexity by 1. So I'm making a little bit of a guess here that that doesn't happen. But if you had a computer program, maybe someone can check for me, see if my claim is right, that this thing actually has complexity 7, or maybe I've just chosen a very unlucky number and there's some more remarkable closeness with a power that drops the complexity down to 6. So let's ask the question, what does this complexity look like as a function of n? If we want to draw a graph of the values of the complexity charted against n. So let's suppose that we have a linear scale here for n. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 all the way up to 10 billion. So arranged in this big horizontal stretch here, nicely uniformly spread out. So 10 to the 9 will be 1/10 of this, so it'll be down here. And then the complexity's values go from 1 up to 10. And a number that's pretty big, this is 10 billion, so a typical number in here might be 5 billion, 348 million, blah, blah. So that will typically have 10 digits. And so we expect its complexity most of the time to be 10. So in this stream here, there will be a lot of complexity 10s. That's our intuition. But every so often there will be a complexity 9, and sometimes a complexity 8, complexity 7, and so on. And the further down we go, the smaller the complexity that we're looking for, the fewer numbers we expect to find with that complexity. So in terms of bands of blackness, this would be very dark band, this would be somewhat lighter band, and then this would be an even lighter band of black. And so as we keep going down here, there would be fewer and fewer points. It would become grayer and grayer, more and more white as we go down. So that previous graph was really very special, because that 10 billion is, in the large scheme of things, a relatively small number. We're only looking at a very, very tiny part of this idea of complexity. So what happens if we zoom out somewhat? Say we go out so that here we have not 10 to the 10, but 10 triangle 10. 10 triangle 10 is much bigger than 10 to the 10. I remind you that 10 triangle 10 is 10 to the 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 10. And if we add 23, we get that number z that I talked about occasionally. And so z will be just adjacent pretty well to 10 to the 10. Okay, what does this complexity look like now for this? Well, a lot of things are quite disconcerting about this graph. Okay, and there's a lot to be learned about mathematics and number theory by thinking about this graph. It's well worth your contemplation of it. Even though we don't know what it looks like precisely, but even the rough features are still very illuminating. So first of all, let's ask ourselves roughly what are the complexity of most of these numbers in here. So we have a tower of 10s, 10 to the 10 to the 10, 10 of them in this tower. So, okay, roughly speaking, if we if we want to count how many digits such a thing has, we should take its log base 10. Okay, and roughly speaking, the log base 10, although we don't need to know precisely what this is going to peel off one of those towers of tens. So we're going to have roughly 10 triangle 9 as the level of the complexity. So the level of the complexity, although it's much less than this, is still, from our point of view, very huge. So that's a big difference from the last picture. In the last picture we had a relatively big number here, 10 billion, but the complexity was only 10. Here we have a super duper number, and here's a super number, but this number is already very big. And so just to orient ourselves, this is not to scale at all, okay? So I'm distorting scale dramatically here. Let's put somewhere here the number 10 triangle 4. 10 to the 10 to the 10 to the 10. That's a nice number for reasons we'll see, because it's kind of at the scale of the universe in some sense. I'll be more precise about that in the future video. But roughly, if we put a little marker here to represent this number, now this was actually linear scale, this number here, this marker would be so close to 0 you wouldn't be able to see it, but let's put it a little bit further away so we can see it. And similarly, we'll put a similar marker on the vertical axis. So there's 10 triangle 4 in that vertical axis as well. Now, what happens to the complexity of numbers? Well, when we have very small numbers, and the complexity is, of course, very small, sort of ranging around here. And as the numbers get big, well, the complexity starts getting big too. And what's going to happen is that, okay, it won't take long before the complexity of these numbers gets pretty big. So there will be lots of sort of random little jiggles here, which if you took a microscope and looked at a little area, you see lots of little jiggles going up and down in an almost crazy way. But, you know, roughly, for most of this range, you would have a complexity which was, you know, roughly around this level, whatever that is. And every so often there would be these dips. Some of them would be small dips, and every so often a more dramatic dip, represented by some line that comes down like this. So a line that comes down like this is telling us that, you know, at that point there we have bumped into a number which is expressible in triangular or exponential power notation much more efficiently than the previous one. It's like bumping into a pure exponential power or a pure triangular power. Okay? So when we bump into one of those, then the complexity plummets down very dramatically. From the one to the next, there's a huge drop. And then after that, it creeps up. We've seen that it only increases by 2 at most. So going from one to the next one, there's only a range of 2 up there. So, but because of the difference in scales here, that still amounts to going up in our picture rather dramatically. Okay. So we would see these spikes, and of course it would be much more complicated than this, but okay, something like this. It has a kind of fractal aspect, perhaps one might say, certainly some kind of random aspect, and it's very hard for us to get a hold of things. But what I want to draw particularly to your attention, okay, is that there's a little band down here. Okay, I put a band across at this 10 triangle 4, which is 10 to the 10 to the 10 to the 10. And I'm claiming that this band more or less corresponds with the visible mathematical universe. What does that mean? Well, that means numbers that can be written down with at least some hope of expressing them in the known universe. So 10 to the 10 to the 10 to the 10 is a huge number. It's a huge number. So this is a huge complexity. So if a number comes down to this complexity here, it's still going to be, in general, very, very challenging for us to write down that number. But nevertheless, this is now within the range of possible expression. We might be able to, by creating some huge hard drive that spans galaxies, at least theoretically, think about trying to express that number. In other words, write down that arithmetical expression that actually gives it the complexity that we're talking about. So numbers that have complexity in this range are accessible to us. At least theoretically. Okay, practically most of them aren't. Practically there would be a much smaller line that we have to draw here, but we're being generous here, and sort of theoretically there would be this band. And the reality is that you can see here, at least if things are in the direction that I'm claiming they are, that the vast majority of numbers are outside this range. Only every so often does one of these branches come down, and then there's a little island of accessibility that's there for us to see. Like when we have a number 10 triangle 10, or 10 triangle 10 plus 23. We're going to talk more about this because I want to quantify this. So I want to be more precise about what I'm saying here and not just have some loose intuition, but I want to actually make a concrete statement that will clarify exactly what I'm talking about here. Okay? And will make it very clear to you that what I'm saying is really quite accurate in the sense that most numbers between here and 10 triangle 10, okay, are essentially inaccessible to us. And this has all kinds of ramifications for number theory, for arithmetic, for what we think about when we think about the mathematical world based on the natural numbers. It's really a disconcerting, destabilizing point of view. But it's reality. It's the way the world is, the world in which we're living in. So next time we're going to quantify this kind of behavior. We're going to see that most big numbers are inaccessible to us. And that's going to have all kinds of ramifications. It's going to force us to examine what actually we mean by a number. It's going to be a consequence of this investigation. So interesting but disconcerting stuff. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.